So one of the most useful skills that you can pick up from in scientific quantitative analysis is the ability to look at and manipulate the units that are attached to the numbers. This is called the factor label method. And once you get it, it seems very intuitive, but it seems to me that nobody is born knowing how to do this. So you might have to work at it a little bit to get it. Say we have a number which is a velocity in units of kilometers per hour. And then we want to convert that into different units of meters per second. Instead of trying to remember a formula to do that, we can actually use the kilometers and the hours and meters and seconds to construct the formula that we need to do the conversion such that make the units work. So we'll start with a velocity in kilometers per hour. Say we're driving along and it's 100 kilometers per hour and you want to know how many meters per second that is. So we need to find factors that can convert these units into the ones that we want. And so let's start with the time units. We want to convert from hours to seconds. And so we'll start by writing a factor which can cancel out the units of hours here and give us something shorter. And I don't remember in my head how many seconds there are in an hour, so I'll write it out. Do this in 2 stages. That there are 60 minutes in an hour. And so now we can cancel the units of hours here. And that's the first step in our factor label method. Now, because an hour equals 60 minutes, if you take a quantity which is the same on the top and the bottom of a fraction, then that quotient is equal to 1. So by multiplying our original information, which is 100 kilometers per hour, by this conversion factor, we're just multiplying by 1, and so we're not actually changing the value at all. We're changing the units, and so that changes the numbers, but the actual quantity stays the same. So the next factor will be from minutes to seconds. There are 60 seconds equals 1 minute. And so now the minute units are gone away, and we have kilometers per second. So that's getting closer, but now we have to deal with the kilometers to meters. And so the conversion factor here is a kilometer is equal to 100 meters. And I have to put the kilometer on the bottom, I can see, because I have to cancel kilometer here and end up with meters on the top. So after we have constructed this whole thing to cancel out the units, meters, so we're left with what we want, meters per second, all we have to do is multiply the numbers. 100 times 1,000 divided by 60 divided by 60 gives us this answer. And so the units have told us how to do the math. So energy comes in units as well, and these are going to be a pretty fundamental currency that we'll be talking about in this class, so we'll pay special attention to them. The fundamental unit of energy, an amount of energy, the unit that I find the easiest to envision is the calorie. A calorie is the amount of energy that it takes to warm up 1 gram of water by 1 degree centigrade. So a gram of water is about a milliliter, so about a centimeter on each side, about the size of a plump raisin. If you make that 1 degree warmer, the amount of energy it took to do that is 1 calorie. You see calories on the dietary labels of food, and it's a kind of a weird thing. Dietary calories, by convention, mean kilocalories. A kilocalorie is 1,000 calories, so, you know, little factor of 1,000 there in your diet shouldn't throw you off too much, I hope. And then the energy unit that we will use most in this class, however, is joules. And a joule is just 1 calorie is equal to 4.18 joules. So a joule is just a constant times the calorie. It's like inches and centimeters. They're analogous, they're the same dimension, but they are different units. So we'll get some practice at slinging units around by trying to deconvolve this very curious unit that shows up on our electrical bills, a kilowatt hour. So a watt is a rate of energy flow. It's in units of joules per second. So if a joule is a quantity of energy, a watt is a rate of flow of that energy. So a kilowatt hour means that we have 1,000 watts of power flowing for a period of 1 hour. But we can simplify this considerably because there are time units in here twice. I'll show you what I mean. So we can simplify this down actually just to joules. So first we'll attack this kilowatt. A kilowatt is equal to 1,000 watts. So now we can cancel the kilowatts. And a watt is defined as 1 joule per second. Now this is kind of a strange looking fraction because you have a fraction bar here at top and a fraction bar down there. So we can actually simplify this by writing second down here and getting rid of this bit. That's what this joules per second up on the top meant, is a second has to go down below. And then we've got hours and seconds. We can cancel those time units, but only after we get them into the right unit. So we'll go 60 seconds equals a minute. So the seconds go away, and then 60 minutes equals an hour. The minutes cancel, so now we just have hours and hours both cancel, and we are left with the only unit remaining is joules, a quantity of energy. So when you get your electric bill, this is the quantity of energy that you have consumed, but there are these obtuse units. We can simplify them to the more straightforward units of joules. And the number comes out to be a big one. There are different ways that you can write this. Scientific notation, the way we normally write it with pencil and paper, would be 3.6 times 10 to the 6th power. That would be sort of shorthand for this 3.6 million written here in long notation. So some of the answers in the exercises in the Coursera site have large numbers like this, and it's kind of a hard thing to type out that many zeros. You have to count how many there are, and it doesn't accept notation like this with a times 10 raised to an exponent. The way computers express scientific notation is like this. 3.6 e to the 6th means 3.6 times 10 to the 6th. Or another way that this could be expressed that would also be valid would be 36 e to the 5, because there's no decimal point here. Then it's 36 plus 5 zeros, like that. So global warming is ultimately about heat, but have you ever thought about what heat actually is? Heat is an expression of the amount of kinetic energy that the atoms in a substance has. So when atoms are moving around very quickly, that feels hot to us. And if they're moving very slowly, that feels cold. Which is amazing that you can feel that at all, because atoms are such tiny things. You can't feel individual atoms. You can feel huge collections of atoms in a solid surface like this, but an individual atom you can't really feel. And yet, how fast that atom is jiggling, you can feel that instantly, because if you touch it, the fast jiggling of the atoms will bump up against the atoms of your skin and make those jiggle more quickly too. And if they jiggle too quickly, they can actually rip apart the chemical bonds of your skin, and that's how you burn yourself. And that's why we have evolved to be able to sense how fast the atoms are wiggling around. So it's like we have little atomic speedometers in our fingertips. It's really cool. So it turns out that each mode of motion of the atoms contains, on average, 1/2 kT of energy. So this is actually how the temperature is defined. This T is the temperature. K is the Boltzmann constant. It's just a number you can look up in a book that doesn't change. So if you have a gas that consists of single atoms, not in molecules, like argon is in single atoms in the air, that thing is flying around in space. And because there are 3 dimensions of physical space, it turns out that a single atom gas like this will tend to have 3/2 kT of energy, one for each of the 3 dimensions of physical space. And then if you have a molecule like oxygen, one of the main gases in our atmosphere, O2, has 2 atoms, and these 2 atoms can vibrate relative to each other. And so that vibration sets up another mode of motion that the molecule can carry heat. And the fact that it's now sort of a line instead of a point means that it can rotate as well. And there are 2 different dimensions of rotation of this. So you get 2 rotational modes from this atom as well. So if you think about thermal pane windows, where the whole point is to stop heat from being transferred from the outside to the inside, the very best thermal pane window that you could get would have 2 panes of glass, and then it would have a vacuum in between, because then there would be no way that the jiggling atoms of this pane of glass could touch the jiggling atoms of that one and transfer the heat by conduction. Unfortunately, they can't make windows with a vacuum inside there because of all the pressure from the atmosphere pushing in. The panes of glass would get broken. So what they do instead is, for the good windows, they put argon between the 2 panes, because an atom of argon, so it goes to the warm side and picks up some extra kinetic energy, and then it goes to the cold side and gives it off, and that's heat loss from the window. But argon can only carry a relatively small amount of energy compared to if you put oxygen into this pane of glass. When it comes to the warm side, it's like a bigger battery. It can carry more energy. It goes from the warm side to the cold side, and it would carry twice as much energy per molecule because it has more modes of motion.